I'm going to talk about where AI is today and provide a framework for hopefully understanding where AI will go into the near future. I'm also hoping this framework will help resolve a paradox that currently exists. So two things are happening at the same time. On the one hand, certain capital allocators are somewhat disappointed about AI progress in the last 12 months. So you have places like Sequoia and Goldman Sachs writing, where is the demand for all this CapEx expenditure going? There's not that much market use or interest for the AI products currently being generated, right? At the same time, within the scientific community, there's above expectation progress in AI, and the expectations are already very high. And this isn't like people in computer science or AI itself talking their book. This is from scientific fields as diverse as climate science to structural chemistry. Problems are being solved that were considered science fiction 24 months ago, right? So how are these things happening at the same time? And I hope to explain it. Now, to understand the future and where AI currently is it's helpful to understand its recent history. So in this chart here, you see a quick history of AI. And the yin and yang between two different schools of thought about AI. The first one in orange is it's what's called connectionist methods, and it's basically based on the idea of induction. The second one in blue is symbolic methods, and symbolic methods are based on the idea of deduction, right? And then on the y-axis here is the proportional log scale of the scientific publications from one school versus the other. As you can see, other than for a brief time in between where symbolic methods dominated, it is all connectionist methods now all the time. Basically, everything you've heard about generative AI is all connectionist methods. So what are they? They start with a very simple idea. They say, give me some data. Doesn't matter what that data is. It could be a bunch of words. It could be pixels from an image. It could be macroeconomic statistics. And then just tell me what you want to predict. You could want to predict the next word. You could want to predict the next macroeconomic print, or is it a picture of a cat or dog? And in the middle, the algorithm will do its thing. It could be a black box. It might be hard to interrogate, and you'll make a prediction. And if you give me more compute and more data, I'll get better and better at it. And if I keep doing this enough, I'll get intelligence. That's the conceit, right? The symbolic method school says, well, there's more to life than just induction. There's also deduction. So what you got to do is write down formal logical systems and then deduct from them, right? So a canonical example of this is your calculator. Your calculator cannot make a mathematical mistake. The reason is it knows the rules of basic arithmetic. Now, it didn't learn those rules. Someone wrote down those rules, a human being, and provided them to a calculator. And unless there's a hardware failure, it cannot make a mistake. Right? So that's a deductive system. A canonical example would be an expert system, right? Is a symbolic system. And the most commonly used today in generative AI systems that are connectionist are deep learning, right? But now it's deep learning all the time. But remember this tension between induction and deduction, because it's going to play out for the tension and the paradox I was talking about, right? So these connectionist methods have had amazing progress this century. So this chart across a bunch of benchmarks in this century shows progress from zero, like your 0% performance, to the dashed line, the horizontal line, which is human level performance. So the beginning of the century, when the start of my scientific career, things were like pretty normal. So you wanted to do handwriting recognition, right? So in the year 2000, you're like 0% performance. And after 12 years, you've reached human level, which is like in an academic generation. And no one really noticed, other than the US Postal Service, for which it was quite transformative, but no one else really cared that much. Then came speech recognition, right, which took us even longer. And then things started changing quite rapidly. The thing was, Fei at Stanford put out a benchmark saying image classification. Tell me, is it an image of a cat or a dog? And they thought this would take a generation to get to human level performance. It only took a few years. And then once you had image classification, then you had image reasoning. And then came language, right? Language understanding and reasoning, and it just screamed to above human level performance. And the last thing on this chart in red here is math. And I'm going to talk about that a little bit because it's very instructive. And this math benchmark is on competition level math questions for middle and early high school. So not the most difficult things that we can imagine, but they're above basic arithmetic. They're like algebra and geometry. In 2001, AI can only score 6% of human level performance. And the authors of the paper who put out the benchmark, former colleagues of mine at Berkeley, they had a very disappointing conclusion. They said, well, I think to do well in this benchmark, we're going to need new science. And the reason that's disappointing is you can't time new science. You don't know when von Neumann's going to come around. You don't know when Einstein's going to have a 1905 year and publish a whole bunch of transformative papers. New science you can't time. You can time technology and engineering, right? But the beginning of this year on this benchmark that we thought we needed new science for, you're above 94% of human level performance on this benchmark. So, and all it took was just scale. Just give more compute, more data, and just use the usual tools of the connectionist method, this thing that we thought that we need a breakthrough through, you don't need a breakthrough for. I'm going to return to this math thing in a bit, right? So the thing that's culturally captured the most attention is language. And I think culturally it's captured the most attention because we're used to like other entities on the planet running faster than us, being stronger than us. But until these language models came out, there was nothing on this planet that could speak language like we could. We thought that was the thing that made us uniquely human. Well, it turns out machines can now do it, and they can do it above human level performance. And again, the time and the speed has been quite impressive, right? GPT-2 came out in 2019, and it was like in grade school. It couldn't count to 10. If you asked it to give you 10 reasons for something, it wouldn't give you 10 reasons. It'd be 5, it'd be 15, it'd be terrible reasons. And if it gave you a complete sentence, you were very happy. So it's in grade school, right? But by 2023, you have the performance you see here on the right of high level, above average human level performance on tests that we thought were cognitively loaded before AI had these achievements. We have this tendency that once a computer can do it, we think it must not be a cognitively taxing test, right? But if you look through these, we all thought they were. You know, the first one here I'm going to talk about is like the AP biology one. This is the advanced placement biology one. This is the one that once it got 85th percentile, was the test result make Bill Gates go long generative AI. They said, well, that Bill Gates thought would take a generation to get, and it didn't. It took OpenAI 6 months of work to do it. Right? You know, the law school admissions test that is taken for people who with a post-secondary, with a college degree to go to law school, it scores 88th percentile, which is above the average score of almost all American law schools. Right? The most impressive test result here is the neurosurgery board exam, because this was not in the training data. So what are the neurosurgery oral board exams? First, neurosurgery is the medical specialty in the United States that has the longest training time. So these are people who have had an undergrad, a medical degree, a residency, a surgical subspecialty fellowship, and this is their last exam. And it scored 83%. No human scored above 90 in a decade. And this is a high pass. And when this paper came out that showed this, it was in a paper from one of the labs. So in a meeting with the deans of Harvard and Yale Med School, and they just turned white. They're like, medicine's never going to be the same. Because this is not a memorization test. It's a test of differential diagnosis and reasoning, right? That they think is very, very difficult, right? So we've had these amazing advances in generative AI. That being said, almost all of the economic value from machine learning has come not at all from generative AI. It's come from just traditional machine learning. I'm going to predict things, and it's mostly come from planetary scale machine learning systems created largely by American tech giants. So what you're Amazon, you're using machine learning to create a global supply system, right? And you're going to optimize and estimate demand and supply curves from your suppliers to consumers so you can match prices. Right? You're Google, and I am going to create machine learning techniques and models to target ads to you. And I'm Facebook, and I'm going to do the same thing, right? So on and so forth. And this is the giant, these planetary scale systems, which you've never had before, work around the world, and they take that value and they bring it back to the United States in general, and the San Francisco Bay Area in particular, right? And if you're NVIDIA, using machine learning to generate your next generation of chips. Right? So why is most of the value with them? Well, these tools are very hard to work with. They require a lot of capital and a lot of scientific expertise, right? And scientific expertise is hard to A, gather, and B, then motivate, and then put to productive use, right? So Large language models, the thing that's captured the current movement, they're very hard to work with. The current limitation, the key limitation they have is they have difficulty thinking step by step. They have a lot of knowledge, so they're very smart in the sense that they have a lot of knowledge. These systems know a lot about the laws of thermodynamics, and they also know a lot about Rosencrantz and Guildenstern, two characters in Hamlet. The number of human beings who know both of those sets of pieces of information is exceedingly rare. They have those, so they're very smart in that sense. But they're not very intelligent of the sense of saying, I'm going to give you a logical puzzle, you got to go think about it step by step, and you got to remember what you're doing. They fall apart. They're not very good at that. That's why currently, like to say, I want to use large language models to help me design software, they're like co-pilots. They're like programmers can use them as a programmer starts typing, it will suggest how to finish their lines, and that's useful. But how that works its way through the economy or a given company is going to really depend on, hey, do programmers want to use it? Are they going to adapt their way of programming that's going to work with this? It's very difficult. What you cannot get them to do currently is be like drop-in remote workers. Because what would you like? Much like you would hire a remote worker to work for you in Spain or India or wherever, and just tell them, please fix this bug, or please add this feature, right? Or please create this software. They can't do this because they can't think that long about any particular task. So they can't behave like what's in the lingo called agents. They do not have agentic behavior. So the thought about 12 months ago in Silicon Valley was, okay, we know this, but what's going to happen is we'll take the large language models, we'll give them a lot of tools. They actually can't do math, which is not what anyone would have predicted, but they can't. But we have calculators. We'll get them a tool of programming, and we'll give them like all these other tools, and then pretty soon they'll do back office stuff for me. They'll write complicated code, and maybe they'll solve a lot of my business problems. The problem came that their attention span is so limited, kind of like a goldfish, they can't even use the tools effectively, right? And if you want them to try to use the tools effectively, you need a lot of scientific expertise and usually a significant amount of capital to solve your problem. But who has that mix? If you're Google, you can do this. And if you're a scientific lab and your problem is protein folding, or your problem is I want to find a new antibiotic, you can do this. But if you're Ford or you're basically anybody in the economy, you can't do this. You're not set up for it, right? So until you get that expertise, it's going to be very hard for you to use that technology, or unless the technology gets easier to use. So all the foundation labs know this. Google knows this, Anthropic knows this, OpenAI knows this, Mistral knows this, Meta knows, they all know this. So they're like saying, hey, we're going to try to make these tools easier for people to use. And there's two ways they can do this. The first is just scale, right? The thing about this revolution is the stupidest thing works. What's the stupidest thing? I'm going to give you more data and more compute. Now, it turns out it's not trivial to do that, but it's not like you need Albert Einstein. You can just do it, right? So we're going to do this. And much like ChatGPT 2 couldn't count to 10 and ChatGPT 4 can, it's not like we invented a new algorithm. We just gave it more data and more compute. So we'll just keep doing that, right? So that's one bet. The second bet is okay, now we're going to actually try to be clever. And we actually have to have an idea. And our idea is we're going to build in reasoning, kind of like from that symbolic school from AI that we kind of forgot. Maybe we shouldn't have forgot about it. And we got to put in this step-by-step reasoning, right? So those are the two bets. And I'm going to talk a little bit later, like the new model from OpenAI that just dropped last week is about the second bet of algorithmic reasoning. It doesn't have any more scale than their previous model. They're working on that too. It just has reasoning in it, right? So that's where we are. So there's two possible futures for AI in the near term, right? The first one, the bullish case will be, all the labs are working on it. The entire scientific community that works on these problems are working on it. We'll just get large language models to be agentic and to be able to plan. Even if they got no smarter than they currently are, right? They have above human level knowledge on a whole bunch of things, as I just showed you. But if they could just plan, this would be great. We could add a lot of economic value. And then companies wouldn't have to reorganize themselves. Much like you have to manage an external team in Spain or or India, you would have some management tasks, but it's not like your workers would have to be different. It's not like you have to go hire an army of PhDs, et cetera, et cetera. The technology would flow pretty easily and products would get induced. So that's the bull case, we'll get there, right? So people are working on that. Okay, see that doesn't happen, then you have the less bullish case, but that's still very transformative, which is no, to get this technology to flow through, it's gonna be a long grind. Like every other general purpose technological innovation in human history has been a slow grind. And it's gonna be like electricity. Electricity came. So factory owners said, hey man, I have electricity. I'm gonna replace my steam dynamo with an electric one, because that's the thing I'm supposed to do. They did it. Negative productivity hit. Why? Because the steam dynamo literally did more work, because it had more force than the electric one you got. So actually, all your machines didn't work well. So it was a negative productivity hit, and they're like, man, I spent all this money and my productivity's gone down. And then someone got the bright idea, but hey, unlike the steam one where there's one big one, the electric ones, I can like hook them up in parallel and I can move them around my factory floor. In fact, they don't even have to be in the same building, and I can get a lot more work done then. Okay, that took 25 years to do, right? Because land use has to change, the factories had to change, the workers had to change, everything had to change. Right? So you actually had a negative productivity hit from people switching to finally got the positive one, and it took massive capital allocations from the end users and retraining. And that's how most technological innovation's gone through human history. That's going to be the base case, unless we fix this agentic problem, right? And the base case is still really shockingly optimistic, right? And fast. If you go back to the math thing, I said, 2021, scientists were like, man, we got to get some new science. We don't know. These things can't solve math, right? So the beginning of this year, right, if you scored these large language models in the most difficult math test, competitive math test we give, which the International Math Olympiads, GPT-4 got 0%. It can't get a single question right. Well, that's okay. The model human can't get a single question right either, right? But not a single question got right. And some people thought, oh man, this is going to be a generation of work. DeepMind said, I got this, right? So by this year, you'll have gold medal in the geometry portion of it, 83% earlier. The latest model gets 100% of the geometry questions right, right? So now we can do Euclidean proofs without fail, when no AI system on Earth did it 6 months ago. Got 0. Go from 0 to 100 in 6 months. And now it's in a silver level across all of the International Math Olympiads, which includes algebra and number theory. And these tests are hard. Like these tests are like so hard that if you took the modal human and you gave all the training you want, spend $1 billion on the modal human if you want, they are not going to get a gold or silver or bronze in the International Math Olympiads. They're as likely to do that as they are to win a gold or silver in the 100-meter Olympics, right? So these are like hard things. And now they're at silver, everyone's betting, the betting markets show the same thing. By next year, the AI systems are gonna be gold. Now to make it work, you have to be Google DeepMind. You have an army of PhDs, you have a lot of capital expenditures, and now you solve this previously unsolvable problem, right? That's what it took. But that's why the scientific community is excited. It's like, wow. That's why you have Terry Tao, arguably the greatest mathematician alive, probably the greatest mathematician in the last 50 years, looks at these models and says, hey, they're now getting as good to be almost a mediocre grad student, right, in math. But that's high praise. You have an AI system that's a mediocre grad student in math, and you're also, the person saying it is arguably the greatest mathematician in like half a century. So that, a year ago, it was like not even close, right? So you don't need Google level of CapEx, but you do need expertise. The other example I have on here is we've been losing the war against drug-resistant bacteria because we're running out of antibiotics. There's an economic story there in and of itself, but we are. So, and we've only like classified as humans for all of human history of chemistry, 100 million molecules. So a group at McMaster, which is a Canadian university at Stanford, got together and said, hey man, why don't we get AI to go through 30 billion possible molecules? Unimaginable for humans to do this, right? And see if it can do something. So if you think about the innovation effect of AI, it's not like replacing a task for humans could do. Humans have no way of doing this before. And you're like, okay, we're going to do something humans cannot do and see if generative AI can do it. And they don't have Google DeepMind capital. They just have a lot of expertise. So they did it, right? And they created a system. It goes through 30 billion possible molecules. It proposes 56. They take it to a lab. 6 of them work and actually kills the drug-resistant bacteria, right? And at a hit rate of 6 wins out of 56 proposals is way above human drug discovery rates. And that's all like happened in the last few months. So that's like the bull case of like, even without fixing this planning problem, you're getting amazing results, right? So, but we want to make the technology easier to use. Remember, there's 2 things doing. One is scale, and one is improving the algorithms. So the scale thing is at work. So if you look at the last few years, the amount of compute given to these algorithms is going up by about a factor of 4 a year. It's sped up recently, so it's closer to a factor of 5. So you're getting an order of magnitude improvement, 10x, on compute every 2 years, right? Along with that comes large growth in capital expenditures. So if you want to think about it this way, ChatGPT 4, right, got trained in 2022. It got released in 2023. It was trained in 2022. The data center cost to build the data center to train ChatGPT 4 was $400 million. If you Google it, the number $100 million usually shows up. That's kind of the least cost of it for train, not the build cost of the data center. It's $400 million. All right, that sounds like a lot. But we're already building $10 billion data centers. There's already been leaks of, say, Project Stargate between Microsoft and OpenAI for $100 billion data centers, right? So the scale thing is working away. Now, are we going to continue getting the returns to scale? Because as scale has gone up, performance keeps getting better. We don't know until we try, but the capital is so far going in, and so scale is going to continue. But it's not just scale that's doing it. We're getting better at the algorithms. So there's been innovation up and down the supply chain, and this innovation is almost entirely happening in the United States. Like San Francisco Bay Area by itself is more important than the rest of the world outside combined in this field, right? The people just don't fully get that. Right? If all of Europe and Asia disappeared, it's less important than the San Francisco Bay Area for innovation in this space, right? And the information's getting to be locked down. And in this chart, if you look at when you see the compute going up, how much is from the hardware side and how much is the algorithmic progress, it's still the hardware side. So that, think of NVIDIA, right? That's the compute scale. But that blue is growing. That's the algorithmic progress. That's like, no, we're actually going to like get better ideas instead of just compute. And now what's happened in the last few years, that's now gone silent. You're not publishing those papers. Now, it's not like the scientists working on it are sitting there at Los Alamos in the desert in Nevada and not like communicating with the Germans, because you bump into them, people talk, people move around in companies, so the information's not super secret, but it is somewhat secret. No one's writing the papers, and it's pretty quiet. So and then this new model from OpenAI is all from the algorithmic progress side. And that is also where the companies are working very hard to say, that is what we're going to lock down. That's going to be our IP. The national security apparatus is woken up and saying, you should better lock that down. Please lock it down. So if this, even in this less bullish case, the period of AI we're currently going through might be the quiet period, in a sense that this part here of the algorithmic progress is not the one anyone wants to be released. The companies don't want it because they think it's that IP. The national security establishment doesn't want it because that is your national security now. All right? And you need that to keep the scale continuing and also keep the planning problem. All right? And then the other thing that's happening from the major foundation labs, the ones who are creating the big models, they consider an existential risk. So they're spending more than on average, and they're all converging. right? So in this chart, Anthropic is not on it because we just don't have the data, but you see like OpenAI and you see Google, they're going about 5x a year. Meta, Facebook started behind, so it's going at 7x a year. Elon Musk's XAI is not on this chart, but it would just be a straight line up because it started from nowhere. And they're all like converging on the amount of compute. And we know from what's called the scaling laws in AI that as they converge on the compute, their performance should start equalizing. And that's what we see, that if you look at when a model's released and their capabilities, they keep leapfrogging each other, right? Until this latest model from OpenAI got released last week, the best model was from Anthropic's Claude. It was better than the previous model from GPT-4. And then for a brief time, Google spun up there. But they keep leapfrogging back and forth. It's very hard to predict who's going to win here, right? Because the biggest players are because they consider an existential risk to themselves, are putting the capital to do it. So much of this is about just the compute allocation you have, so it becomes very hard to predict who's going to win. Now, the different players have different incentives in mind. For scientific applications, by far, Google DeepMind is ahead. That is just what its passion is. It's the one that solved what's called the protein folding problem, and then just gave the information away to the world, because their idea is to transform medicine, not to monetize the protein folds themselves. But they haven't produced their best models for consumers or businesses. While OpenAI and Anthropic, because of the way the business is structured, need to do that, so they do produce the best models for people at the end, right? So in summary, what's happening is, I hope, do you understand why the scientific community is very excited, even the scientific community that doesn't directly do AI, because they have the expertise to do all that work to control these models that are very hard to control, right? And why also then the business community is like, well, I'm not sure how to use it. I'm not sure how to get the value out of it right now, because the expertise is not there to make maximum use of the current technology, right? So, but they'll eventually get there. Either the slow pace, which is more experts will be developed, they'll flow through the economy, and slowly but surely, much like electricity, if you look back 10 years from now, the economy's transformed. Or it will happen very quickly if the foundation labs and the technology can solve this planning problem. Like early reports from this OpenAI model is that it's much better at reasoning than previous models. So it is like a step trying to solve towards the bullish case, which they're trying to work on, but it's still a long way to go, and it's very hard to predict which of those two will win.